All right, so let's see. DNA replication. DNA replication is in preparation of doing mitosis. Okay? The double helix is going to start unwinding from its histones. What's going to happen to do this is that the DNA helicase is going to open up where it's like where those hydrogen bonds are between the bases. Since they're easy to break, the helicase is going to open up that area, like almost like taking a zipper and unzipping it, so you have two strands on either side. So you're going to have see how I'm showing it? It's like it's unzipping. And helicase is going to come in here and start unzipping this area. Okay? So we call this a replication fork. There's a fork there. Let me just do something really fast. Now, a few things are going to happen over here. All right? There's your DNA helicase that's happening over here. It's unzipping this. And we've got to make, there's A's and T's and C's and G's on either side here. Does that make sense? Okay? Now, I'm going to try and keep this short but sweet because I don't want to go into details about this, but I want you to understand what's going on. There's something called a 3' over here and a 5' over here, 5' here, and 3' here. This 3 and 5' thing could get confusing, but each sugar is made up of a ring. And there's 6 carbons on there. The carbon is here, 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 and here. When we open this up, each one of these has numbers. All right, dealing with chemistry. This, I'm just giving you numbers. This could be, let's say, let's say it's carbon 1, carbon 2, carbon 3, 4, 5, 6. They have numbers for each one. And what happens here is that somehow this kind of breaks up here so that there's going to be, when it breaks, there's going to be a 3' here. This is where carbon's, the third carbon will be on here at this point. Because remember, there's a carbon, or there's a sugar here, a sugar here, a sugar here, and so forth. And then there's phosphate in here and so forth. So what's happening here, when we open up this one end, the carbon number 3 is the free end over here. And the free end, when these come together, the 3' end over here goes with the 5' end over here. Okay? If the 3' end is at this end, the 5' end is at the further end up here. You'll understand when you get to biochemistry if you're going to go into there, but you have to understand this a little bit, at least to deal with words like 3' and 5'. Okay? As the helicase comes in here, it opens up. And we're going to start needing to build a new strand of DNA. We've got to make a duplication of it. We have the formula here. This is A, T, T, A, okay? So we know what we can build on this side. And we're going to end up making a DNA over here and a DNA over here. Making two. You're duplicating it. Does that make sense? Okay? What's going to do that is that, in the way it's building it, is that this is going to be a 5' end, building it this way. So it's going to, let me see. And who's doing that is something called DNA polymerase. I got a video to show you this too. DNA polymerase is going to start building this new strand of the DNA here. So DNA polymerase is going to read the exposed bases. It's going to read it 3' to 5'. It's reading it this way, the black here. It could only read 3' to 5'. This has no problem because as this is opening, the DNA strand is being built over here as it's opening. It's another one could build here, another one could build here, and so forth. It's right behind the helicase. That makes sense? Okay? The problem is on this side. It's reading 3' to 5', but it's writing 5' to 3' because 3' will be over here. See it? It's reading the black, but it's writing the orange. So it's going this direction. And that's not a problem. This is what we call the leading strand. Okay? It matches with the nucleotides on there. So that's the one leading strand, and that is not a problem. It's going this way. However, this strand has a big problem. It still has to read it from 3' to 5'. So it's reading it this way. Three prime is up here, so it's reading this way. So it's going to start building it here. So, but they're going to be in fragments. Because as this is going up, there's going to be a gap here and another one has to be made. So they're going to be in, you'll see with a video. We call these Okazaki fragments. And we call this the lagging strand. You're going to have segments, these fragments. There's a fragment here, and then there's nothing in the middle. And we have another enzyme that comes in called DNA ligase. Ligase means to tie. And the ligase will come in here, and it's going to tie this part here. Ligase will come in here and tie these two things together. And you'll have another break over here. Okay? So what's happening here is that this leading strand is built up here. There's not an issue here. DNA polymerase is going to build that there. It's reading 3' to 5', but it's writing 5' to 3'. As helicase is opening, this strand is being built right behind it. There's not an issue there. Here's an issue, because as this is opening up, we could start the polymerase over here, but then you just have a gap over here. So you have these gaps that are happening here. So the ligase is going to come in afterwards and fill in the gaps, tie those things together. These are called Okazaki fragments, and this is the lacking strand.
When DNA replicates, its strands are separated by the enzyme helicase. Single-stranded DNA binding proteins keep the strands from reannealing. One DNA strand encodes the leading strand, which forms from its 5' to its 3' end, using DNA polymerase III. No problem here, but the lagging strand presents problems. It has to form from 5' to 3' too. It forms in pieces called Okazaki fragments. First, an RNA primase lays down an RNA primer. Then, DNA polymerase III lays down new DNA. The process repeats again and again. DNA polymerase I replaces the RNA primers with DNA. Finally, DNA ligase links the Okazaki fragment.
Okay? Alright, so let's see what we can do with the next part. Well, a few other things about this. Okay? It happens very fast. DNA polymerase happens very fast to do like 100 base pairs per second. So you have thousands of DNA polymerase that happen all at the same time. If you need to make, let's say, 1,000 copies of a certain test, to have one Xerox machine to do that, it's going to take a long time. But if you have, let's say, 20, it happens much faster, okay? And all the 46 chromosomes are replicated in 6 to 8 hours. That's how fast it does this, okay? So the speed is due to the DNA replication occurring at multiple. We just have one part over here, that's it. But we could break it up. The helicase happens here, happens here, happens here, and so forth. So we could have this happening simultaneously in different parts of the DNA. You could have one, you could have like, actually probably hundreds of them all happening on one chromosome. Okay? And that's why this goes so fast.
So like when the helicase is okay, so it forks,
Mm-hmm.
and then when it finally reaches the point where it forks again, does it keep on forking, or does it stop at that point?
No, then it goes back. Then it well, eventually it'll fuse. The ligase will actually fuse them together.
Okay.
Yep. The ligase will do that. And what happens here is that we call this semi-conservative, right? This is what's happening. You got this unzipping is happening here, and you're going to be putting in the polymerase. The DNA polymerase is going to put in these that match the bases up here. All right. So you get two new daughter cells from one parent cell, and we call this semi-conservative, meaning that what's happening here, we're not going to get. Let's say this is one DNA. We're not going to get, it's not going to break up into this, and then the new stuff over here. What I'm saying is, you're not going to keep this the way it was and just make a copy of it. You're going to have what we call semi-conservative, meaning, and you'll see it from what I did over here, that when this duplicates, you're actually going to get this kind of setup. You'll get 2 daughter chromosomes, but it's part of it was original and part of it's new. Not this setup where there's going to be, the original is going to stay there and you're going to have a totally different one. All right, so we call it semi-conservative. Okay? This kind of setup. Okay? But I want you to see what it would not be, which is the upper one. Okay? So if you think about it, if one strand of DNA has the, and don't answer it, just give it a moment, then I'll ask you to raise your hand. If one strand of DNA has the base sequence of this, the other strand will have the sequence of what? Give it a moment. Don't call it out. Give it some time for other students to think about it. All right, who thinks A is the correct answer? B, C, D, E. Oh, he's the answer. Good. Okay. Not too bad, right? Yeah, but you're going to ask questions about this, not that. Well, yeah, we ask questions of both, though. I understand that. Okay. Errors and mutations. DNA polymerase does make mistakes. Okay. It's not perfect. But there's a lot of corrections, a lot of ways that it corrects on itself. In biochemistry, you'll start learning about those things if you're going into that realm. But the result is only 1 error per billion different bases replicated. But it does make mistakes. But we have checks and balances to fix that. So the mutations, changes in DNA due to replication errors or environmental things. If radiation comes in there, or viruses like I mentioned, or chemicals, they can do that. If any changes, it can actually cause ill effects, or no ill effects, like you won't see any differences. It may kill the cell, may become cancerous, may have genetic defects that will affect the future generations too, okay?